it's a good day. The light was green crossing the highway this morning, so that's how I know it's going to be a good day. I know, right?
What set of notes is this at? 7.1?
Sorry?
Where can I find them? What are the notes called
on? They are in the slide section, and we're doing chapter 7 today, starting chapter 7. And I didn't like her slides, so I snuck in some of my old ones. That's why they're different, but that's okay, right? Okay, and then I wanted, before we get started, wanted to highlight, although I think you guys have it, I'll post a video for the next two sections, 7.2 and 7.3, but we need to do 7.1 today so that we kind of have the lay of the land, and then you're ready to fly on your own or watch this video. I'll post it after class today, and that's instead of class on Wednesday. So you can watch it whenever you want, or, I mean, you don't have to watch it. You can just learn the material if you want, whatever you want. But we will review it on Friday, and so you'll need to kind of have a good understanding of it, and then we'll just jump in and do some practice problems on Friday.
You don't have class on Wednesday?
No class on Wednesday.
Okay.
Just this video. That's a perfect amount of time too. So, well, it's 2 minutes over, but that's okay. I know, rude. And then I let loose with the stickers, so don't forget test. And then we have test number 2 on April 2nd. Next Wednesday.
Yes.
All right. Here is a screenshot of our Moodle. So today we're going to do 7.1, where we finally get started with inference for numerical data. Very exciting. And then for, hey, this is Tuesday, Thursday. That's wrong, but I think you get the gist. Video only for Wednesday. Good morning. Which will cover 7.2 and 7.3. So just like we did with proportions, right? We're going to start with one sample mean. How can we compare it to one value, right? Some hypothesized value. And then we branch out. And what if we have 2 samples? And for means, it's pretty typical that we have a special case of 2 samples where the data is paired, right? Kind of before and after studies, right? Where we've made 2 measurements on the same subject. That's going to be paired data, or just 2 independent sample means that we want to compare, just like we did for 2 sample proportions. And then for proportions, we kept going, right? We did the chi-square goodness of fit for 3 or more, and then we did the chi-square test of independence for a 2-way table. But for means, we're not going to cover 3 or more means. I will post a bonus assignment so you can try it. Yeah.
Would you say that this part is more difficult than the last one, or do you think we'll be able to understand it better because we've done it?
My hope is that this is going to be like, oh, this is just kind of the same thing that we've been doing this whole time. And so
Similar?
very similar. We're still going to do hypothesis testing. We're still going to do confidence intervals.
Okay.
And then, yeah, I just forgot to change the days here, but hopefully that's not throwing anyone off. If it is, that is a different kind of concern. Yeah.
With the bonus assignments, are those counted for marks, or is it like if we've done a bit poorly on one assignment, that kind of brings up the grade?
So yeah, so Steve, who teaches the other section, we debate this all the time. Because I do kind of a cheater version of the bonuses where I just set it to drop however many assignments that I give you bonus assignments. So it just drops your lowest, 3 or 4 or whatever assignment grades. So if you don't do the bonus assignment, then it gets dropped, right? Whereas, and ideally, right, a bonus assignment, you would be able to go beyond 100% on the assignments, but Moodle doesn't accommodate that easily. So I do it the easiest way I know how. And so it just drops the lowest number of however many bonus assignments I've given. Right.
So I recently got like 30 of one because I got totally stuck.
Yeah, and so, yeah. And it's important to remember there are some big assignments and there are some little assignments, right? And they're all worth the same. So kind of play the field. Usually the bonus assignments are kind of small, right? To kind of encourage you, because you do have to learn the stuff or kind of read up on it on your own. And so I want to reward you for that. But yeah, if you do the bonus and you do well, it'll replace a lower grade. Yeah, kind of slot it out. Okay. I put a lot on this slide before we even got started. Rude. Chapter 7. In chapter 6, well, chapter 5 and chapter 6, we were doing inference, which is hypothesis testing and confidence intervals. In chapter 5 and 6, we were doing it for categorical data, right? We had some proportions, right? 320 out of 600 students felt this way, right? That kind of thing. But now we have numerical data. Time to dust off the numerical data. Remember in chapter 1 when we talked about the variable types, and I said, okay, well, one way to really figure out if it should be a numerical variable or a categorical variable is, does it make sense to talk about the average, right? And so for numerical data, that is what we're going to analyze. We're going to analyze the average. So we analyze the average or the mean. I usually just use whichever term. Oh, no. Yeah. That won't do. My body fails me towards the end of term. Come on. It actually always happens. It's either my hand or my voice. My body can't keep up. It's a young man's game. So I use whichever word, sounds better, but it's your job to know that these two are interchangeable, right? The average and the mean. And you can use whichever one you like. Yeah. So 7.1, this is going to feel like kind of back to basics in a way, because we started with one sample proportion, right? And so now we start with one sample mean, and we introduce our third distribution, the t-distribution, right? And if you don't have a t-table with you, I brought some extras. And I can't wait to force people to take their test back at test 2. Look at all these. One day. After the final exam, I'm always hunting someone down. Grab your tests, I don't want them. So if you need a t-table, let me know. But this is a new distribution. It is going to feel very familiar though, right? So before I do the whole lecture on this one slide, so far we've applied inference techniques to categorical data, right? Proportions. Yeah. And so now we're going to talk about numerical data. Yeah. When we analyze numerical data, we often want to analyze the mean. This bar is off, but that's okay. X bar. Or the average. X bar is the sample mean, right? And so X bar is the sample mean. But we use that sample mean, right, to learn about the population mean, which is mu. Mu is the population mean. Versus, so maybe here I'll do numerical data. And here I'll do categorical data. Kind of an afterthought, sorry. Then we were using the sample proportion p hat to learn about p. The sample proportion where p was the population proportion. Right, so we collect a sample in both of these scenarios, right? And we try to learn about the population parameter, right? Any measurement from the population is called a parameter. And any measure from the sample is called a statistic. But I already said that. So, okay. Hi, Baba. Should we go to our formula sheet? Maybe. It'll have everything we need. So we're on the second page of your formula sheet. We're just gonna crunch through this thing. I know when I handed it out, it probably felt like a lot. And it is a lot. But we go through it kind of nice and sort of slow. Okay. Just like before, whenever you see this X bar follows a normal distribution with a center at mu and a standard error of sigma over root n, right? We know how to read this. And so this here is the standard error of X bar, right? So our point estimate is going to be our X bar. Estimate is X bar. And the standard error of X bar is going to be sigma over root n. Sigma is the population standard deviation. And here it makes it more obvious why we needed a different name for the standard error, right? Because if you talk about, okay, the standard deviation of X bar is the standard deviation of your X's divided by the square root of n, that gets a little boggy. So then we change the terminology. But changing that terminology hasn't been obvious in the proportion case. But now when we see, okay, there's a standard deviation involved, and what are we supposed to do with that? What can we call it, right? And so this is the population standard deviation of X. And so the standard error of X bar is the standard error of the point estimate. Okay. We've had this trouble before, right? If we go back to the one sample proportion situation, let's go back here. We had p hat follows a normal distribution centered on p, and then the square root of pq over n. And then we said, well, I'm not going to have p because I'm trying to learn what p might be. So then we said, well, how about I just use p hat instead, right? Or better yet, if I have a hypothesized value, then I use that. Okay, but we used something in place of p. Notice that we only had to replace one thing here, right? Because we replaced p with p hat, right? My best guess. And then again, same thing. Q is just 1 minus p hat. So I've only really replaced p with p hat. And then n is from my sample size. So I didn't need to guess at that. Okay. The problem today is that we can do the same thing. Our best guess at mu is x bar. But we also don't have sigma, right? And so my best guess at the population standard deviation of x is going to be my sample standard deviation of x. And so our best guess at mu is x bar. I shouldn't say equals because they're not the same, but I should say is x bar. And sigma is S, the sample standard deviation. Standard deviation of x. But now, and then n is from our sample, and so we know what n is. Okay, so that's nice. So I'm guessing at two things from my sample. So how I think about it is if you have to pat your head and rub your belly at the same time, right? Because both of those things are coming from your sample. And so we need a test statistic that can handle all that variability, right? And so it is a normal distribution, sort of. But because I have to use guesses for both my mu and my sigma, right? This is what turns it into a t distribution. Since we are guessing, I'll say guessing in quotes, because we're not really guessing. We're using our sample to estimate it. But I think guessing kind of makes more sense in this case. Since we're guessing two values instead of one, we use the t distribution. Okay. T is going to depend on the sample size. Okay. And I'm sure I have a lot of notes here, but T depends on the sample size. Or maybe I should say the shape of T, because we've already seen that. The shape of T depends on the sample size. We've seen that with the degrees of freedom for a chi-squared, right? It's going to depend on, okay, how many categories are you comparing, right? And then now it's going to depend on the sample size. And so I guess we'll start from the bottom. Now we're here. The degrees of freedom is going to be n minus 1. Let's just get that out of the way. So clean that up. Not much better. So the shape of the t distribution depends on the sample size. Now, as the sample size increases, as n increases, t is going to morph into a z distribution. T approaches the z distribution. So everything we learned about the z distribution still applies. We're just gonna have slightly different values for our t, but everything else stays the same. We've got this unimodal symmetric distribution, and as long as your sample size is big enough, then it's gonna look basically like a Z distribution, right, which we've seen. So what if we kind of take a deep dive here? If I want to make a confidence interval, right now I'm trying to learn about what mu is, right? I'm trying to capture the population mean. I use my point estimate, right? X bar, plus minus the critical value. Now this is a T star, and this subscript just says the degrees of freedom is n minus 1. You don't have to write that if you don't want to, if you don't like it. But T star is taking the place of Z star. It's just saying how many T's do I need to move out to make a 95% confidence interval, right? Or how many standard errors, I guess. S is our best guess at sigma divided by root n, right? And so this is the standard error of X bar. Or maybe I should say the standard error of the point estimate, because just to highlight that the layout of our confidence interval is the same. We have our point estimate, right? Our best guess, plus minus, and then we move out some number of standard errors of the point estimate. And then this is the critical value, which is the value that sets our confidence level, right? We've been seeing 1.96, 1.645 for a 90-degree or 90% confidence interval, that kind of thing. Okay. So you basically know how to make a confidence interval, basically. That's cool. We just need to learn more about T, but there's really not a lot to know beyond what we've said. We'll do examples, of course. As long as you remember that you're doing confidence intervals to try to capture the population mean, and you're doing hypothesis testing for the population mean, right? You're trying to learn about the population still. That's the same scenario as for proportions. This feels familiar, right? My null hypothesis for a one sample mean question is that mu is equal to some mu naught, where mu naught comes from the question, right? The mean we want to compare X bar to. That's going to be from the question. Huh. This looks sort of familiar, right? If we remember way back when we were first starting this stuff, we were working with Z as X minus mu over sigma. Right? But now I have a mean and a hypothesized mean, and instead of my sigma, I need to use the spread of X bar instead, right? And so X minus mu over S over root n. I'll remove this because it's not part of it. But I wanted you to see the similarities. But then when we replace the X with an X bar and the sigma with an S, right, it turns into a T. And so we're going to calculate a T test statistic, which I find really difficult to say. T test statistic. What's fun is when you do a hypothesis test for a mean, we calculate a T. And so out in the real world, right, If someone says, oh, you're taking stats, oh, t-tests and stuff like that, right? You'll say, exactly. Right, and so usually these are referred to as t-tests. A t-test. It's a hypothesis test using the t-distribution, which means that it's about the average. Tough when I use means in a different way there. Which implies a hypothesis test for the average. As you can imagine, a lot of data analysis is about the mean, right? Average, anything really. Average speed, average income, even though it's skewed, but we'll have a way to deal with that. And so we'll be able to analyze averages even from skewed distributions, okay? As long as our sample size is big enough. So that's kind of cool. And so we're going to calculate a t, which again roots back to, okay, we need to know how t behaves, but we have a good idea already. And then our test statistic, right, is our t-test statistic. Does the same thing. How far is my point estimate from my hypothesized value, right? Taking into account the spread of my point estimate. What's really nice, in my opinion, is that notice how you have S over root n here, and you have S over root n here, right? Whereas for proportions, we use different things, right? We use mu or P naught, Q naught, right? Versus P hat, Q hat, and you had to keep track of those while you have the formula sheet, but still, right? And so now, what's nice about means is you just really have the one standard error, right? S over root n for one sample means. Cool. Okay. I crammed a lot on there. So I think for our conditions, as long as our observations are independent, right, which we can assume independence if the sample was randomly selected, right? That's the same as before. So far, that's been a condition for all our hypothesis tests and confidence intervals, and that's going to stay that way. And so if the sample was randomly selected, so first we have our independence condition. Same as before. And then it gets a little bit different, right? Because we have means instead of proportions, and so, but we have to have independent observations. That's step number one, which we can get by randomly sampling. And the population distribution is not extremely skewed. If it's extremely skewed, then you might want to employ different methods. And as everyone loves to hear, beyond the scope of this course, right? Past us. And so as long as the population is not extremely skewed, which means we'll be able to handle some skewed data, right? Income and house prices and things like that. We can still analyze those averages. So then, and a large sample. And so we're going to assume n has to be greater than or equal to 30. there's some wiggle room there. Depending on the field, I've seen it pushed to 20, right? In biology especially, it can be really difficult to randomly sample observations. And so then they say, well, okay, how about I just assume I'm sampling from a normal distribution, which they usually are. And then we can decrease the sample size a little bit. Okay. But for us, let's use a sample of size 30 as our cutoff. So this would ensure that the sampling distribution of the mean is nearly normal. So that's good. Right. Independent, and I'm sampling from a population that's not extremely skewed, and I have a large enough sample size, then I can assume that it's nearly normal or is going to follow the t-distribution. And then we'll be able to assume that the standard error, right, S over root n is reliable. And that's because we need a large enough sample size for our standard deviation to kind of have settled down a little bit, right? Otherwise, there's a lot of variability in our small sample sizes. We did a central limit theorem. I guess it's been a while. CLT is the central limit theorem. We did the central limit theorem for one sample proportions, and then we just said, okay, how about from here on out, we just assume that whenever I give you, hey, it follows a normal distribution, you can just assume that's true, right? In theory, we could go through and do the same things where we randomly sample from a known population and we generate all those sample statistics, and then we look at that distribution, and we can do that for means as well. I'm not going to make you do that though. You did it once and that's plenty. So the central limit theorem states that the sampling distributions will be nearly normal. Okay. It holds true for any sample size. Okay. So that's really nice. So not just sample sizes larger than 30, any sample size as long as the population distribution is nearly normal. So if you can reasonably assume that you're sampling from a normal distribution, which a lot of things are, right? Weights, speeds, heights, distances, whatever, right? They're going to be normally distributed. Grades, right? All those things are normally distributed. And so then, as long as you're able to assume that the population distribution is nearly normal, then you can use any sample size. You could have a sample size of 10 if you wanted, as long as you say, I assume that the population distribution is nearly normal. And so, right, this is kind of difficult to handle. How do I know if my population distribution is nearly normal? But now you know to argue it if you have a small sample size, right? Just like I said, a lot of biologists, right, if they've got 20, then they say, well, I am sampling from a normal distribution, so safe. And then they publish their articles and move on. And like I said, usually they are sampling from a normal distribution, right? Mosquito sizes and things like that. Okay. I don't really care about this, but okay. It's on here. I guess I cared about it at one point. But I think these might be 10 years old now, so thanks. No, I don't care about that. Grown lazy, I guess. Okay. So the conditions that we have to check are, do I have a random sample? Right. The data come from a random sample of size n from the population of interest or a randomized experiment. Okay. So either way, as long as it was random in some way, then you can assume that they're independent. I'll kind of add independent here, even though I have it down below. The population has a normal distribution. In practice, though, it's enough that the distribution be symmetric and single peaked, unless the sample is very, very small. And then this is kind of a one that I don't really care about anymore. This one's optional. But the population must be much larger than the sample, say at least 20 times as large. That's the same as the N has to be less than 10% of the population condition, which I also made optional, right? Because if you have the choice of getting a huge data set, right, or collecting a huge data set, as long as it's randomly sampled, I think, you know, that's great. You're gonna have more reliable estimates. And so putting a cap on your sample size is kind of silly, but technically there is a cap. So when these conditions are satisfied, then X bar has roughly a normal distribution. And so we've already seen that it follows the T distribution instead, but it's because we don't know sigma and we estimate it using the sample standard deviation.
Oh.
We used to teach it, okay, well, what if we pretend that we know the population standard deviation, right? And so, but we've outgrown that, thank goodness. I always thought it was so ridiculous, but a lot of old textbooks still taught it that way. So, but we'll never know the population standard deviation, right? Sigma. So why is that? Because in that scenario, at some point, you had collected data on the entire population and you wrote down what sigma was, and then everything else you lost it, but now you're trying to collect a sample to learn what the population mean is. Why didn't you just write down what the population mean was? Then you'd know. Anyways, pretty silly. What's nice is it would follow a Z distribution, but here we get the T distribution. We're ready for it. The T distribution is always centered at 0, just like Z. The distribution also has a bell shape, okay, but its tails are thicker than Z. If we think about, okay, the area under the curve is a probability, right? Then if I have thicker tails, it just means that the probability of having these more extreme values is a little bit bigger than for a normal distribution. And that's because I'm estimating X bar and I'm estimating S, right? And so for this reason, right, observations are more likely, right? The probability is higher to fall beyond 2 standard deviations from the mean than under the normal distribution. And this is what it'll look like. So here, the dotted line, we have our normal distribution, which is our Z. Still centered at 0. Still centered at 0. Both of these, they're unimodal, they're symmetric. But now if we look at our T, look at this, look at this, look at this. This area, right? There's additional area there. The area under the curve is the probability, right? And so the probability of more extreme values, and maybe I'll put it down below. The probability, which is the area under the curve, of more extreme, I'll say test statistics. Is higher for T than for Z. Right, so I usually kind of, the area under the curve is still 1, right? And so what happens is if I have a sample of size 2, then I have these huge, huge tails, right? Then it would look something like this. Because it doesn't know. I have a sample of size 2. There's nothing I can learn from that. Right? And so, but what happens as your sample size increases, right? We said our T distribution is going to get pushed up, and therefore the tails are going to get pushed down. Right? So it approaches this Z distribution as our sample size increases, leading us to the degrees of freedom, which we've already seen a version of for chi-squareds, right? We've seen degrees of freedom for chi-squareds, but also now we're going to have degrees of freedom for the T. So the T distribution has thicker tails for small sample sizes, and the tails get thinner as the sample size increases. So this is what we said before, right? Or we could say, as n increases, T approaches a Z distribution. Is really what we're saying. And so the degrees of freedom are how we communicate the sample size to the T distribution. Just like for the chi-squared, it was how we communicate, well, how many categories are you comparing here? Right? And so for one sample mean, we're going to have the degrees of freedom is n minus 1, right? Sample size minus 1. That's on your formula sheet, which we've already seen. Subtle differences. Here, I have degrees of freedom 1, which means that my n must be 2. And there's a sample size of 2, and it's still, you know, there's still kind of shape here, right? It's just making a lot of room in the tails because my estimates can't be relied upon, right? And so I need to make a lot of room in the tails, but it still has that similar shape. And you would never collect a sample size of size 2, right? That's crazy. Even degrees of freedom 2 means that I have a sample size of 3, right? Degrees of freedom 5 means I have a sample size of 6, right? N minus 1 is the degrees of freedom. Even a sample size of 6 is kind of ridiculous, but that's this, oops. That's this line. Oh, that's a huge one. That's this line here. And this is Z. So you don't need a huge sample size for everything to kind of behave the way that we're used to. In fact, by a sample of size 11, right, we're here. And then technically, at a sample size of the population size, or infinity, if you want to think about it that way, then you reach this pinnacle. So the difference between these last two is pretty small. effectively. N is infinity. So between 11 and infinity, it behaves kind of the same way, right? But we have a t-table to tell us exactly how. And how. Any questions before we talk about the t-table? I think you could probably pick it apart right away. Because is your sample size going to change from one question, I should say? It's just going to be the same, right? You collect a sample of 45 students, right? And you find that their average height is something, right? Your sample size is going to stay fixed. So then you can find your degrees of freedom, 45 minus 1, 44. But let's take it back a step. So we're going to use the t-table. This is old. We actually have been using the t-table already. Will be the same. Just because I found that it was a huge leap to go from the z-table. You can find the p-values using the z-table, but we've been using the t-table, and so that's nice because we've already seen it. And so to find the p-value, so this is all kind of gearing you up to a different table, but you've already seen it. We've already worked with it quite a bit. To find the p-value of a t-score, right? So a t-test statistic that you've calculated in step 2 of your hypothesis test, we follow these steps. So you calculate your degrees of freedom, which is n minus 1 for one sample. And then in the left-hand column of the table, you find your degrees of freedom. Once you have your degrees of freedom, you can't stray from this row. And do I say it? I'll bring in the table, because now, oops. Copy. Oops. Okay. So calculate your degrees of freedom, and then in the left-hand column, find your degrees of freedom. You can't stray from this row. Now, our table looks like this, right? This is our t-table, the t-distribution of critical values. And here are our degrees of freedom. It goes nice and breezy, 1, 2, 3, all the way up to 30. It moves by ones. Here, goes from 30 to 40, 40 to 50, 60, 80, 100, 1000, and then Z. And we know that as your sample size increases and becomes the population size, then you approach Z. That's cool. So we see that in the table here. But there's a rule. Let's say that you have 44 degrees of freedom. Right? You always have to round down. 44, you probably would go for the 40 line instead. Right? And of course, software can just handle any degrees of freedom. This is just a condensed version. But I think some of the assignment questions ask you to use whatever you use for the table, just otherwise it might not match. Okay. And so here, if you're choosing between, let's say you have 990 degrees of freedom, then you're choosing between 100, let's say degrees of freedom is 990. You're choosing between 100 and 1000. And for some reason, it feels so painful, but you have to use 100. What? I know. Is there a difference, a practical difference between them? No, it feels weird, right? But we have to use 100. Use degrees of freedom equals 100, because what does using degrees of freedom of 1,000 say? That means you're claiming to have a sample of size 1,001, right? But you actually only had a sample size of 991, right? And so you're kind of making your estimates sound more reliable than they are, right? And so it's kind of a false advertising. And so to play it safe, you always round down. Where can I'll start this note. If the degrees of freedom is not listed, we always round down. Right. Otherwise, we're kind of claiming to have a more reliable sample than we actually have. But, right, you can kind of convince yourself that there's not really a huge difference between 0.677 and 0.675, right? And there's not really a difference between 1.29 and 1.82, right? And so, and notice there's sometimes no difference between the Z and the 1,000, right? Just depends on where it is. If the degrees of freedom is, I'm going to put it here too. Can you tell I always have questions about it? What am I supposed to do? Now I've written it twice. If the degrees of freedom is not listed, we must round down. Then we're back in familiar territory, right? So instead of the Z star line, which is the only one we've been working on, now we're on a degrees of freedom line, but everything else stays the same, right? So you're going to move along that row to figure out where the absolute value of your calculated T would fall, right? And then now you have your fingers on the two T-scores that wrap around your calculated T, right? And you should record them just like we've been doing, right? Somewhere between here and here. Now move your two fingers down to the bottom. From the alternative hypothesis, you'll know if you have a one-sided or a two-sided test. I'll highlight that as well. Because even as people are studying for the final exam, I get frantic texts saying, well, how am I supposed to know? How do I know? If your alternative is that mu is less than mu naught or mu is greater than mu naught, you only care about one side. Versus if your alternative is that mu is not equal to mu naught, that makes it a two-sided test, right? You care about both extremes. And now, just like before, now you have a range for either your one-sided or your two-sided test as appropriate, right? The p-value. And you're going to read it from right to left because they're decreasing as you move further out. And then you're going to record the range of the p-values you found, right? The lower p, and then the p-value is between your lower and your upper p. And just like we've been doing, you can still compare the range of the p-values to the alpha level, right? The entire range is either below alpha or it's above alpha. Okay. Same thing for a confidence interval. Let's say, for example, I've collected a sample of size 27. Then I have 27 minus 1, so 26 degrees of freedom. I picked one that is on this table. Now, if I want to make a 95% confidence interval, right, my critical value, instead of 1.96, we use 2.056, right, because I need to move out a little bit more to capture the central 95%. 2.056 and 1.96 are pretty similar though, right? Roughly 2. But you have to use those specific values. It's okay. You don't have to know what a p-value is. I'm actually pretty happy if when you see a p-value and you think, you know what, she has said that a lot. And you have kind of an understanding, okay, I need that to do my hypothesis test. And you don't need to know what it is yet. I'm not expecting that of you. If you do understand p-values, that's great. But they're notoriously difficult to get a handle on. But once you have a handle on them, then they're not going anywhere, right? They all behave the same way. But if you don't know what a p-value is, then you can ask me because it's okay. And with that, we're ready for an example. Crazy. Any questions before we do an example, though? Before we do an example, I know, example. How about we cruise through the sections of the formula sheet that will be introduced in the video? And I think I mentioned it before. The video calls it chapter 5, but that's just because we're using a new edition and there's kind of a jumble. And so it is chapter 7, but it used to be chapter 5. For paired data, what if you ignore all the subscript diffs? Because now we analyze the mean difference, right? And I'll talk about why in the video and all that fun stuff, but this looks like x bar plus minus t star times s over root n. That's the exact same thing. So it's just morphed into a one sample proportion, one sample mean question proportion, right? So if you just ignore all the diffs, it's the exact same thing that we just talked about, one sample mean, right? Because I'm gonna generate one sample of differences. Yeah? What's nice about paired data is that we always wanna know if the mean difference is significantly different from 0. That gets wordy, right? But we always compare it to 0. So it's even, I think, simpler than the one sample mean that we're gonna do today, or that we are doing today. So if you just ignore all the diffs, it's the exact same problem, right? So that's nice. How about two sample means? If I want to look at the difference of two means, remember back with two sample proportions, right? We had sample information from both samples that we had to kind of get a handle on. We have the same situation for if I want to analyze mu1 minus mu2, right? If I want to compare those two things, then my best guess at that difference is x1 bar minus x2 bar. Right? And then T star, well, we know how to find T star, right? That's on the T table, right? 95% confidence interval. You need your degrees of freedom, but that's okay. And then the standard error is the standard deviation of group 1 squared divided by the sample size of group 1 plus the standard deviation of group 2 squared divided by the sample size of group 2 and then square rooted. This is the standard error. And if you want to do a hypothesis test, we've seen this before, right? P1 equals P2 is one of the options. Or if you want to think about mu1 minus mu2, because that's technically what you're analyzing, right? How it compares to 0. That's why technically this has 0 there, minus 0. But I don't even write that because who cares? Just like we did for the proportions, right? Comparing two proportions. And what's really, really nice is this standard error is again the exact same as this standard error. Right? The only little piece that's missing is the degrees of freedom. How do we read this? It's the minimum of either n1 minus 1 or n2 minus 1. That's effectively you take the smallest sample size minus 1 as your degrees of freedom. Right? It's just a fancy way of saying it. There. We just did 3 types of questions. You can do them all already. No, don't worry. Back to one sample, but I wanted you to see that, okay, now that I've introduced or we've talked about the T distribution and we're more comfortable with the rest of the T table, you are ready to fly on your own. Majestic birds. I think of myself as like a mama hen guiding you through the stats maze, and you're my little chicks. But now you're gonna fly. The level of dissolved oxygen, which we'll abbreviate DO. Are we ready for the example? In a stream or river is an important indicator of the water's ability to support aquatic life. Feels important. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. And here are the results in milligrams per liter. The mean and the standard deviation of this sample are X bar is 4.77 and the standard deviation is 0.94. Well, probably the hardest part is figuring out what type of question you have, right? And notice there's no mention of a proportion, right? And so now your first thing that when you read a problem is figuring out what type of question you have. And on test 2 for 1 mark, I'll get you to tell me what type of question it is, right? And you can just use the headers on your formula sheet. That's fine. Because my goal is to point you in the right direction and then you stay there on your formula sheet, right? So in terms of the type of question, it's numerical data, right? I have these measurements in milligrams per liter, right? 4.53, 5.04, 3.29. That looks numerical to me, right? And so that tells me it's a means type of question. It's about a mean. In fact, you're given a sample mean and a standard deviation, a sample standard deviation, right? So given a sample mean and standard deviation, as soon as you see a standard deviation being given, the only way I could do that is if it's a means question, right? If I have numerical data to calculate the standard deviation with. And so it's a mean question. But then as we saw, we're gonna have choices, right? Is it a one sample mean or is it two samples? If it's two samples, is it paired, right? Are those paired? Two observations on one subject, or are they independent samples? Now here, I only have one sample mean, and so it's a one sample mean type question. One sample mean type of question, right? Only given one X bar. If I give you the mean of group A and the mean of group B, then you have two sample means, right? And so that'll tell you, okay, then I have a two sample means problem. I want you to spend some time just reading questions and trying to figure out what type of question it is. And so I'll post the practice 4 test 2. It's really long, okay? And that's because I want you to have seen so many different types of questions and be able to read them and figure out, okay, that's that type of question, that's this type of question, that's this type of question. And so you can do kind of a fire drill, right? Read the question, what type of question is it? Right? You can do them as well for practice. I had a few people text me asking if I could post it earlier, but I don't like to do that because until we've seen all the material, otherwise I'm just getting texts all the time. I don't know how to do this problem. It's because we haven't done it yet. So, but I'll post it. And then maybe I'll make it so you have to watch the bit, or at least mark the video as watched before it appears. Rude. Because I don't want people asking me if they haven't done all the material yet. Okay, so we have numerical data, we have a sample mean and a sample standard deviation, right? I'll always give you those things. And then we're ready for the question. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. That's bad. Is there evidence that the aquatic life is at risk at the alpha equals 0.05 level? This, right, when we see, is there evidence, that tells me I have to do a hypothesis test. Okay. For a one sample mean, I'll do a step 0, the conditions. For a one sample mean, we're really only going to check that, okay, if I have sampled randomly, then I can assume independence. So independence it said that it was randomly chosen locations along a stream, right? And so we can assume that these locations are independent of each other. They're all in the same stream, but that's because I care about knowing about this stream, right? So that makes sense. The locations were randomly selected. So that's good. For our, we can call it the normality condition just to match how we've been naming them before, right? Our sample size is small. 15. N is 15, okay? And once we hit 30, it doesn't matter if we sampled from a skewed distribution or what, then, so that's nice. But before 15, we have to assume we sampled from a normal distribution, right? So N is 15 is less than, bless you, is less than 30. So B, so we must assume that these measurements follow a normal distribution. So we assume dissolved oxygen levels follow, I guess I should say in the stream. In the stream follows a normal distribution. One of the ways that you could check it is you could make a histogram of your data. And if that histogram looks reasonably normal, then it's safe to assume that you sampled from a normal distribution, right? But we're not going to do that. Too much on the conditions or the assumptions, right? Sometimes we're just stating the assumptions that we're making. We ready for our first means example? I don't count the conditions. Clearly making it step 0. State the hypotheses. You need your null hypothesis? From your formula sheet, you know it should be mu equals mu naught. But we need to replace that mu naught with a value that we want to compare our sample mean to. Right? That value, in this case, is going to be 5. Right? So here, this is going to be my mu naught. It's the value I want to compare my sample mean to. Right? I have 4.77. 4.77 is less than 5. But I'm concerned if it's significantly less than 5. Right? And so there's some wiggle room where, okay, things are basically 5. And then at some point, right, taking into account the standard deviation, then we've moved too far away and it's significantly less than 5. So mu naught is going to be 5. The value we want to compare X bar to. Whatever you want to compare your X bar to, that's your mu naught. It has to be a number and it'll be in the question. Right? Kind of like how, you know, is there evidence that more than 40% of people feel this way, or a majority or something like that? And then we're getting really good at stating our hypotheses, right? It has to be about mu still, and it has to be about 5 still. It's just the sign for the alternative hypothesis that I need. Now we're concerned if it's below 5, right? So less than 5. Making this a one-sided test. In fact,
If it's two-sided, what would it have?
it would be not equal to. Because if it's not equal to, let's see, I'll put 5 here instead. Because if it's not equal to, then you're not just concerned by these guys, you would be just as concerned by the other side as well. Right? So not equal to, then you're concerned about both sides. Versus for this example, we saw a sample mean that is below 5, and the p-value is going to communicate how likely it is to pick up a sample, a random sample that generates 4.77 if the mean is actually 5. Right? And so this is the p-value later, that area. But in order to calculate that, right, we need our test statistic. Yeah. Step 2, do the test. Do the do. Find, calculate the test statistic. Boring. Do the t-test. From our formula sheet, t is x bar minus mu naught divided by s divided by root n. How far is this x bar, our sample mean, from the hypothesized mean of 5, taking into account this spread that we're expecting to see for x bar? So we have t is 4.77 minus 5. How far is that from 5? If the spread is 0.94, s is 0.94, divided by the square root of 15. Kind of a common mistake, and I understand how it can happen, is instead of putting the n, you might put the degrees of freedom. So just if you think you're doing it right, maybe just go back and make sure you're not doing the degrees of freedom here. It has to be the n. Common mistakes. So t is negative 0.23 divided by 0.94 divided by the square root of 15, 0.242706956. I get a t of negative 0.9476448613. You'll want to keep at least 3 decimal places because that's what you have on the t-table. But just for good measure, let's keep 4 in this case. 0.9476 to 4 decimal places. Need at least 3 decimal places to match the t-table. A tea party.
Yeah. So I think of every time.
Hey, that's what we're having today. We're having a tea party. Teas. Cute. So everything you know about test statistics still applies. Right? This is not very far. we use 2 as kind of a threshold, so -2, then we would start to think, okay, I might be rejecting H naught, but moving 0.9476 standard errors below the hypothesized mean is not really that far, right? You have to move at least 2 to be considered, in the danger zone. So now we're ready for step 3, which is find the p-value. First, we need our degrees of freedom. And I like to just articulate what it is that I'm doing, right? I'm about to use the t-table, and so I'm going to say using the t-table, with degrees of freedom equal to n minus 1, right? That's my degrees of freedom for a 1 sample mean question, which is 15 minus 1, which is 14. We find, I'm going to add a page here. And go back up here. I'll go to a clean one, actually. Everyone has a t-table today, right? I guess I'll do it anyways, but 14 degrees of freedom. Then you can ignore the rest of the table, right? We are doing a hypothesis test, and so that means I need to find my p-values down here. And we said, well, because I'm only concerned with it being less than 5, I don't care about it being greater than 5. That seems to be fine, right? So then I have a one-sided p. So what I need to do is I need to maybe tighten this up. Copy, paste, see if I can pull this off in kind of a reasonable time frame. Well, I've already committed. Copy, delete. Paste. Okay. I did cut some of these out. Only kept what we needed. Oops. It shouldn't blot out everything. Okay. 14 degrees of freedom. Now I'm trying to place the absolute value of negative 0.9476. And so the absolute value of t equal to negative 0.9476 is between 2 values. And just like before, right, on the inside track, you're centered at 0, right? So between, if you're kind of on the left side of 0.692, you would be between 0 and 0.692, right? And then you can figure out, okay, well, the area in one of the tails at 0 must be 0.5 still. And the area in 2 of the tails at 0 should be 1. Same thing if you're over on this side of the table, right? If your t is bigger than 4.140, next stop is infinity, right? So then it's somewhere between 4.140 and infinity. And the area in the tail is either between 0 and 0.0005, very, very small, right? Or if it's two-sided, between 0 and 0.001, still very small. You can, if you like the critical value approach, like we did for the chi-squareds, right? We were told to use an alpha level of 0.05, right? And we have a one-sided test, so the 0.05 we'd be using is here versus here for a two-sided test. Then what we could say is my t would need to be bigger than 1.761 in order to reject H naught. Let's use the p-value approach, just because I want to focus on that. If I drop the negative, 0.9476, 0.9476 is somewhere between these two values. So I jot that down. 0.868 and 1.076. I do want to see this, right, your work from the table, because sometimes what happens is if you have jotted down the wrong values or anything kind of silly like that, then as long as I can follow through and the rest makes sense, then I can give you the most amount of marks that I can, despite you making an error, right? And so as long as you tell me what you're doing, right? If for some reason you're having a panicky moment in the test and you're like, oh yeah, it's between these two values. And then you tell me, okay, 0.9476 is between 1.076 and 1.345. I'll take half a mark off, but then as long as you follow through with that, that's okay, right? Because that's what you told me that you were gonna use. Yeah. Then the one-sided p-value I like to use the same signs, but that means I have to read those p-values from right to left, because I don't want to have to think about the inequalities, right? I don't want to have to do any more work. So then, tracing down, same as we have been doing. My one-sided p-value is between 0.15 and 0.2. We can still use this. That's the end of your work for the p-value, but just to think about alpha is 0.05, right? And then your p-value is somewhere between 0.15 and 0.20. So it's all larger than 0.05, right? And you can kind of visualize it if you want. I want to make sure I have room for the conclusion here. So we have our p-value, we have a range for our p-value. Our conclusion is the exact same as what we have been saying. It's just that our final conclusion is going to be about the mean instead of the proportion. Step 4 is your conclusion. And as always, show off all the things that you did and that you already know, right? You had to do a ton of work to get here. Since our one-sided p-value, right? You had to do work to know that it's a one-sided p-value, right? So may as well throw that in there. Since our one-sided p-value is between, right, and you're going to say what it is, between 0.15 and 0.20, it is not less than the alpha level. Less than the alpha level of 0.05. Right? Compare your p-value to your alpha level. If it's not less than the alpha level, you do not have enough evidence to reject H naught. Right? which means we do not have enough evidence to reject H naught. I like to use this simplified symmetry, right? It either is less than the alpha level, which means we do have enough evidence to reject H naught, or it is not less than the alpha level, which means we do not have enough evidence to reject H naught. So then you only need to change those two things and they kind of match, right? And so those are your only two possible statements. Which means usually we want to reject H naught. This is one of those scenarios where we were actually kind of worried that we had to reject H naught, right? Because the dissolved oxygen level below 5, that's bad, right? But of course we have to do this kind of testing to make sure that it doesn't drop below 5, right? If you're doing kind of environmental monitoring and stuff like that. And so is there evidence that the aquatic life is at risk? The null hypothesis is they're not at risk. The alternative is that they are at risk. So when we fail to reject H naught, we're actually happy, right? And so, yay. There is not evidence that the aquatic life is at risk. You can say it however fancy you want, or not fancy. Therefore, there is not evidence to say the aquatic life is at risk. Fish rejoice. Whee! Like, wait for it. Whee! Party time. I guess there's probably more fish. Oh, cute. There. That feels important. Right? And so what we're going to find is it's going to be a lot easier to think of just kind of real world examples for means type of questions. But we do analyze a lot of proportions as well. But in terms of things that you might come upon in your studies or just kind of in life, usually are means type of questions, right? And I know what you're thinking, why didn't we just start with that? Well, because the Z is nice and stable, whereas the T is kind of, you've got the chops now, but that would have been confusing to start with. How about a confidence interval? This one's kind of boring. Business bankruptcies in Canada. Wow, it's really boring. We could do it for the fish. No, let's see another example. Why? Because I want you to be able to read this and tell me why it's a one sample mean type of question. And what's nice is the confidence interval has the same conditions as we checked before. And so really simplified in comparison to the proportion type of questions. Okay, business bankruptcies in Canada are monitored by the Office of the Superintendent of Bankruptcy Canada, OSB. Include in each report are the assets and liabilities the company declared at the time of the bankruptcy filing. A study is based on a random sample of 75 reports from the current year. That's your sample size, right? And so a random sample, that's good. the average debt, which is the liabilities minus the assets, is $92,172. Okay. With a standard deviation of something massive, $111,538. Right? A word of caution, if the standard deviation is bigger than your mean, that's kind of a concern, but we're gonna ignore that. Construct a 95% confidence interval for the average debt of these companies at the time of filing. Okay, so here we go. First thing, right, you're gonna read this question and figure out what type of question it is. And I think I mentioned it, but on test 2, I like to do a mad minute where I just give you little question blurbs and you have to read them and just tell me what type of question it is. Right? Because I can't make you do a ton of these, but I can make you read a bunch of little blurbs and tell me, okay, what type of question? Because then I feel like if you figure out what type of question it is and you can do that correctly, then you can just do all the rest. It's where I usually sing The Sound of Music. When you know the notes to sing, you can hypothesize almost anything. Anyways, why is it? Thank you. Why is it a one sample means type of question? Some clues. You're given a sample mean and a sample standard deviation. That kind of sets you on the right path. Right? Really only one option, right, in terms of is it a proportion question or a means type of question, right? So it has to be means. And then we move on, okay? If it's a means type of question, how many samples do I have? 1 or 2? And then we stop there in this course. You can go to 3 or more, but it's a different test statistic, and we don't have time for that. So I only see 1 sample mean and 1 sample standard deviation. And so that tells me that it's a 1 sample mean. Right. Only given 1 X bar and 1 S. Okay. We can pull out some information here. We have a random sample of 75 reports, so I have a sample size of 75. And then the average debt is your X bar. And the standard deviation is S. We want to make a 95% confidence interval for the average debt of these companies at the time of filing. I'll show you on the formula. I didn't do it for the hypothesis test. I'm just realizing now, but I wrote it out, so hopefully that's okay. I have X bar, I have S, and I have N in the question. So all I need is my T star at N minus 1 degrees of freedom. Right? And so here, read this as T star at N minus 1 degrees of freedom. It's just shorthand. And you don't need to write that N minus 1 if you don't like it. So we need our degrees of freedom. It's N minus 1. I have a sample size of 75. So I have 74 degrees of freedom. I'm gonna go to my table here, 74, 74. Oh no. I'm choosing between 60 and 80. 60, good. Because if you say you have 80, that means you have a sample size of 81, right? Which means that your X bar and your S would be tighter than they actually are, kind of more reliable. And so we use 60 degrees of freedom. And let's see if I can do the same thing as I did before. Copy. And here I'll say, but using degrees of freedom equal to 60. Right? Because we have to round down. You don't have to write it in red, but you should say, okay, what the actual degrees of freedom are, and then what you're going to be using, right? Because that tells me that you understand that, okay, it's not in the table, so I had to use something else, and tell me what that is. So 60 degrees of freedom, oops, pointer. 60 degrees of freedom, and I wanted a 95% confidence interval. Can you believe our luck? Dun, dun. Our T star is going to be a perfect 2. Wow. Crazy. T star is 2.000. Which means I have to move out exactly 2 standard errors around my X bar in order to be 95% confident that I've captured the population mean. Ha. So X bar plus minus T star times S over root N. I don't even write that as subscript N minus 1. It is there. It's proper to put it there, but I skip it. My X bar was $92,172 plus minus 2 times the spread of that thing. So which is the S over root N. And it was 111,538 divided by the square root of 75. Right? So again, just make sure that you're using the sample size and you haven't mixed it up with the degrees of freedom or anything. So here. Now, this is money, so we can round to 2 decimal places. Okay. I'll calculate the standard error first, and then the margin of error. I'm going to jot down the margin of error, right? Just because I want to showcase that it is the margin of error, but also it's nice for checking your work later. So 111,538 divided by the square root of 75 times 2. I get 25758.59773. This is the margin of error. 92,172. That's my best guess. But with money, we can round to 2 decimal places safely. Right? And so rounding properly, we get 60 pennies. 2, 5, 7, 5, 8, and 60 pennies. 25,758. 60. Which means my interval is going to go from 92,172 minus 25,758.6, which is 6,641,340, up to 92,172 plus 25,758.6, 930.6. 0. I think it was in a different class, but you know how like cool coffee shops only do 1 decimal place for the money? It's like $7.50. It really bothers me for some reason. It's 2 decimal places.
I see that in restaurants too, where it's like, you'll see something that's like 8.5, and they don't put a dollar sign.
I know, I don't like it. I don't
think
like
it's a
it.
psychology tactic.
Oh, maybe. It's like, oh, it's
saying-
not money, it's just kind of close to money.
Yeah.
That probably works. So now we have an interval for what? For the average debt of these companies at the time of filing. So we were asked to make a 95% confidence interval, which we did. Now we need to interpret the interval, right? And we say, we use the same framework. And I want you to use this framework for your interpretation, right? Don't stray, don't try to make up your own. It's not plagiarism. It's correct. We are 95% confident the interval from 66,413.40 to 117,930.60 captures, right? This is the same framework that we've been using, right, for all our confidence intervals. And so it should feel pretty comfortable, I hope. Captures the average debt of these companies at the time of filing. The average debt of these companies at the time of filing. All right. Of all the companies, it's implied that it's for the population. And man, you guys are good sports. There.
Isn't the bay closing because?
Yeah, I thought there was another here, like another court
Yeah.
session
They keep almost
before.
closing like every 10 years.
I know.
But I swear I read something and they were down a lot.
Yeah, probably more than our
Yeah,
confidence
yeah,
interval.
I think it was like 900 million or something. It was crazy. Yeah.
Yeah. I'll stop this recording. That's the end of chapter 7.1. And you've got the skills to do 7.2 and 7.3.
Do we have to do